One of the most useful numbers that we can use to determine the type of bond that's going to exist between atoms is the electronegativity. And the simplest definition for electronegativity is that it's the ability of an atom in a molecule to attract the electrons to itself. That's the shared electrons. The second statement has to do with how the electronegativity is measured, which is not so important for us. The trend for electronegativity is that it increases as you go across a period left to right, and it decreases down. The highest electronegativity is for fluorine, which is 4, and the least electronegative atom is cesium. While it's possible to look up the values for electronegativity in a chart like this, it's usually enough just to know where things are, relatively speaking, on the periodic table. So, for example, we see that all of the values over on this side of the table are pretty small, and over on this side of the table, especially with like chlorine and fluorine, oxygen, and so forth, that the electronegativity values are much greater. So if we take the difference between those two, we expect an ionic bond. On the other hand, if we have bonding that occurs between things like carbon and nitrogen or carbon and hydrogen, then the electronegativity values are close together, and we expect the type of bond to be covalent. So in the first case, comparing lithium and fluorine, it's clear that fluorine is the most electronegative atom, and lithium is on the other side of the table, so it's much less electronegative. The reason for that is fluorine has many more protons, and the electrons are all at the same level, at the second level, so that means that the attraction of a fluorine atom to the electrons is going to be much greater. In comparing fluorine and iodine, again, fluorine is going to be more electronegative, so even though iodine has a greater positive charge, it's also shielded, or its attraction for the electrons is much more shielded than is the case with fluorine. So we've already talked about this. The trend is to increase toward fluorine, decrease toward cesium, and the reason for that has to do with both the shells and the shielding electrons, and also the effective nuclear charge. So these are the same factors that influence things like the size of atoms and the ionization energy. So it's the same factors that are involved in both cases. This chart summarizes the relationship between the difference in electronegativity and the type of bond, so that we see that when the difference is 0, then the bond type is covalent, and it's almost 100%, or very nearly 100% covalent character. As we move down and the difference increases, then what happens is the bond type goes from covalent to polar covalent and eventually to ionic. But I think the important thing to realize is that, as with a lot of things, it's a gradual trend, so it's not all or nothing. So you can have a bond that has maybe it might be 20% ionic and 80% covalent. So it's not it doesn't have to be always 100% one or the other. When you have a problem like this and you are trying to rank things in terms of the bond strength, you can always look up the electronegativities and subtract and find the ones that have the greatest difference. Or, and this is more typically what you would be expected to do, you can use the element's location on the periodic table to figure out which ones will be the most or the least polar. So let me suggest that you try and just stop at this point and see if you can go through and do that, and then come back and we'll talk about the answer. So if you look at the first set in A, then you'll see that all of them have fluorine for the second element, so then you just need to compare the positions for nitrogen, oxygen, and carbon. And basically they just go in the opposite direction. So in this case, you are going to go from the most, so that would be here, oops, call that 1, and then 2 and 3. For the next set, you could start here. This one's going to be the least because they are adjacent to each other, and this one is going to be the most, and then this one. And for the last set, we have this one, which is nonpolar covalent, and then these are relatively close, and then this one is further away. Okay, so you should try to do this one before looking at the answer, but at any rate, after you check, if you think about it a little bit, the N and the O are adjacent to each other, so there's a little bit of difference of electronegativity, but it's still going to be slightly polar. And for the last one, if we look at it, we want the one that's the most polar, but it's not ionic. So in that case, you could either, again, you could check the electronegativities, or if you look at the distances that are involved, then this one is going to be the most polar, but not ionic. This one would be ionic over here. Whenever, you can assume that whenever you have a metal and a non-metal, that you're going to have something that is ionic.